Unit 9 is all about right triangles. I wouldn't say it's all about right triangles. The majority of it is about right triangles. We're starting off with the Pythagorean theorem, which you've probably seen in passing or at least heard of. It's named after a Greek guy named Pythagoras. I joked in first hour that I was going to name my first kid Pythagoras, and nobody laughed, so I'm not going to use that joke again. But Pythagoras, he's given credit for this theorem, but in reality, people way before him were doing this in Babylon and China. But he gets credit for it, probably because he's an old white guy, but that's how it goes. Pythagorean theorem. So here's what it says. It's specifically for right triangles. So in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So, in layman's terms, what that means is that leg A, or side A, and side B is a leg. If we square those two values, that is equal to our hypotenuse, or value of our hypotenuse squared. The hypotenuse is always the longest side of a right triangle. It's also always the side opposite of the right angle. When we say opposite side, we look from the angle, we go across the interior of our triangle till we get to our hypotenuse. So what this is really just plugging in numbers, and we're going to have to solve for x when we're doing this. So I'm going to go straight into this first example here. If we're trying to find the value of x, then we're going to write the side lengths as a Pythagorean triple. And I'll tell you what that means when we get there. So, using our theorem, we know that these two shorter sides are legs of our triangle. And this larger side is our hypotenuse of our triangle. So, using our theorem, we can say that this x side squared is equal to 5 squared plus 12 squared. And then we can simplify and then add. So this is our left side stays the same. This would be 25, and this would be 144. So 25 plus 144. Combining terms, we would get 169. So x squared is equal to 169. And then you got to kind of go back to algebra, think, how do I undo to the power of 2? Well, you have to take the square root of both sides. Taking the square root of both sides undoes our exponent. So we're left with x is equal to, this would be 13. So when we write this as a Pythagorean triple, we just write all of our sides from shortest to longest inside parentheses. So we'll say 5, 12, 13. So I'll go your shortest leg, your second shortest leg, then your hypotenuse. This is what a Pythagorean triple is. A Pythagorean triple has to be all whole numbers. So if you were to get out a decimal for a side length, it wouldn't work. It has to be whole numbers. So it's kind of like the best, basic as it gets. Just solve for the hypotenuse. If we're solving for a leg, we're using the same formula, but now we're just setting up our equation differently. 7 is a leg. X is a leg, 14 is our hypotenuse. So we could say 14 squared is equal to, put x squared first, plus 7 squared. 14 squared is 196. So 14 times 14 is 196. That's equal to x squared plus 49. Then we subtract 49 from both sides. So we get 147 is equal to x squared. And then to undo our x squared, just like we did our last time, we have to take the square root of both sides. So we're left with an x. And taking the square root of 147, it is not a perfect square, so we're going to get out a decimal. On big ideas, what it's going to do, it's not going to let you put in a decimal most of the time. It's going to ask for what's called an exact answer. So that means that your answer is going to have a square root in it. So I'm going to walk through how you find your exact answer. And it's, again, something you learned in algebra. So if I was to give you the square root of 147, do any of you remember kind of making a factor tree and finding the largest perfect square that goes into 147? So like you're saying, okay, does 4 go in there? Does 9 go in there? Perfect squares are numbers multiplied by themselves. Ringing a bell at all? Yeah? Okay, good. I got some head nods. So, for example, in 147, the largest perfect square that goes in there is 49. 49 is a perfect square because it's 7 times 7. So our square root rules say we could write this as square root of 49 times the square root of 3, because 147 divided by 49 is 3. Kind of working back up our tree. Yeah.
Can't you just do it on a calculator?
No, because it's a big idea is going to ask for the exact answer. A decimal would be a rounded answer. Yeah. So we simplify one step further. This is going to give us a whole number. The square root of 49 is 7. So this would be 7 square root of 3. So our x value, our exact answer, is 7 square root of 3. If it doesn't ask for an exact answer, you can just round it to however many decimal places it tells you to round to. But this is approximately equal to, take 1/4 the square root of 147. This is approximately equal to 12.1. The little squiggy equal signs means approximate. Approximately equal to 12.1. Because this would be a repeating long decimal. So you just say 12.1. And we cannot write this as a Pythagorean triple because we have a decimal, not whole numbers. Whatever it asks you. I know in big ideas it asks for the exact answer, so you'd write this one. All right. For Pythagorean theorem, whoever made textbooks decided that Pythagorean theorem is the best thing for word problems. So the lengths of the skyscrapers shown are connected by a skywalk with supporting beams. Use the Pythagorean theorem to approximate the length of each support beam. So since these are two congruent triangles, we don't have to do Pythagorean theorem for both. We just have to do it for one of them. So we're solving for x, which is our hypotenuse. So we could say x squared is equal to 47.57 squared plus 23.26 squared. And this is, you'll definitely want to pull your calculator out to do this. It's like 47.57 squared plus 23.26 squared. I just put it all into my calculator at once to eliminate having to round more and more. So I would get out 2,803.9325. So I'm leaving all my decimals because I'm just going to round at the very end so I don't introduce extra error. Because the more you round, probably talked about this in science at some point, the more you round your answers at the beginning of the problem, the more error you're introducing into your final result. So I'm just going to round at the end. So to find out what x is, we just take the square root of both sides. X is equal to I'm going to round it to 2 decimal places since that's what all my other lengths are given in. They're given to 2 decimal places. So this would be 52.95 meters. 52.95 meters would be the length of each of these support beams. So this would be an example where you wouldn't, like your exact answer, like you can't really get an exact answer if you're taking the square root of a decimal. So having a decimal as your answer is fine. So kind of the comparison of when an exact answer is good, when kind of an approximated answer is good. All right. Any questions on the first page? I think it's pretty straightforward, I hope. But if not, we'll shore it up on the backside. All right. If you flip to the back, the first thing I put on there was just the converse of the Pythagorean theorem. So remember, a converse, we're going in the opposite direction. Here, we're starting with the fact we're saying, well, if c squared is equal to a squared plus b squared, then we can conclude our triangle is a right triangle. All right, so now we're given that this is true, and we're concluding it's a right triangle, not the opposite way around. In the Pythagorean theorem, you're saying, okay, if it's a right triangle, then c squared is equal to a squared plus b squared. So in these next examples, to tell whether each triangle is a right triangle, when we plug in our values, we're just checking to see that both sides equal each other. If they equal each other, then using our converse, it's a right angle. So here we go. Our longest side is always going to be our c value. If you would take the square root of 113, you get a repeating decimal, but it would be greater than 8 and 7. So I know this is my c value. So I'm going to say c squared, or square root of 113 squared. We're checking if that's equal to 8 squared plus 7 squared. If we square a square root, it just they undo each other, the two operations. So we're just left with 113. 8 squared is 64. 7 squared is 49. So we have 64 plus 49, which when we add them together, we get 113 out. So yes, using our converse, since c squared is equal to a squared plus b squared, we could say, yes, this is a right triangle. And your right angle would be here, because that's the opposite the hypotenuse. All right, next piece, doing the same thing. 4 square root of 95. This is 4 times the square root of 95. This is our longest side. So we know this has to be our c squared. So we're checking if 4 square root of 95, I'm going to put that in parentheses just to make sure that we're squaring the whole thing. we're seeing if that's equal to 15 squared plus 36 squared. So 4 square root of 95 squared, I would do that. You can put it in just like this onto your calculator. You get out 380. $15 squared is 225. And 36 squared is 1,296. So when we add these, if we were to add this side together, it would not be equal because this is already bigger than 380. So we give this a red X. No, this is not a right triangle, because it fails the converse. If this is not equal, then it cannot be a right triangle. All right, last piece we'll talk about is it's a Pythagorean inequalities theorem. So this isn't specifically for right triangles, this is for any triangle. So it says, for any triangle, ABC, where C is the length of the longest side, the following statements are true. If C squared is less than A squared plus B squared, then your triangle is acute. If C squared is greater than A squared plus B squared, then your triangle is an obtuse triangle. So I just try to associate when I'm doing this. Think acute. Your symbol goes this way. Obtuse. Your symbol goes the other way. So in this last example, the first thing it asks us to check if to verify the segments with these given lengths, it actually makes a triangle. So this goes back to semester 1 material. To check that lengths make a triangle, we said that, well, if we add the two of the side lengths together, it has to be greater than the third, which this is. If we add 4.3 plus 5.3, that's greater than 6.1. We have to check it for all three sides. So we could say 4.3 plus 6.1, well, that's greater than 5.3. And then 5.3 plus 6.1, that's greater than 4.3. So we can verify by doing this that this is a triangle in fact. All right, since we know it's in fact a triangle, we can go through and figure out whether it's acute or obtuse. By doing that, we use our Pythagorean inequalities theorem. So we know that our longest side is 6.1, so that's going to be our C value. So I'm going to say 6.1 squared, and I'm going to leave a gap in between them, and then write 4.3 squared plus 5.3 squared. Why I leave the gap? Because I'm going to go through and simplify, and I'm going to put my symbol in the gap at the very end, because I don't know which side is greater than, which side is the greater one right now. So taking 6.1 squared, that is 37.21. We take 4.3 squared, that's 18.49, plus 5.3 squared, that would be 28.09. And we're to add these two together, our A squared plus B squared would be greater than our C squared value. So looking back at what it says, we said if our triangle, if our mouth, our inequality mouth is facing the right, It's an acute triangle.